Hi, my name's Ambrose, and this is a practice of my thesis defense. My thesis is called Typed Clojure in Theory and Practice. So what is Clojure? Clojure is a programming language that runs on the Java virtual machine. According to a couple of recent surveys of JVM users, it's got between 3% and 1% of the market share of Java JVM users. So it's probably in the top 5 most popular languages on the JVM. So it's a general purpose language. Here's the results of a different survey, this time of Clojure developers, and you can see that there are various applications of Clojure, mostly web development, but the usual suspects for a general purpose language. So why would you choose Clojure over a different language? Well, that same survey asked Clojure programmers that question, and the top 5 answers are sort of grouped into 3 neat categories. The first is this idea of functional programming with immutable values. So using values and first-class functions, you can easily write pure functions, and it's quite expressive. So second, we can take advantage of experimentation and rapid prototyping by using the REPL, and the dynamic typing of Clojure makes it quite easy to reload code and that sort of thing. And finally, we can leverage the host that Clojure is hosted on. So in this case, it's the Java virtual machine. We can basically use any library that is written in Java, which gives a lot of opportunity for writing expressive Clojure programs. But however, there are frustrations with Clojure. And this same survey asked what the frustrations were with Clojure itself, and of the technical frustrations, my take on it is that Clojure programmers need help specifying and verifying their programs. So the number 2 complaint you can see here was that the error messages were poor, and there were suggestions to have better tooling and that there was no static typing. And that leads to my research, which is creating an optional static type system for Clojure called Typed Clojure. And it's had a good response in the industry since I've created it in 2012, and I've been working on it since, giving talks at industry conferences and crowdfunding money, and also mentoring students for Google Summer of Code to enhance it. But this is how Typed Clojure works. You take an existing program written in Clojure, here's a hello world, and then you add type annotations to all of the top-level functions. So say hello, takes any, and returns a string. And then you use the type checker to verify the Clojure programs. And this happens statically. You don't actually have to run the program. So Typed Clojure deduces that this program returns a string without having to run it. So my thesis statement involving Typed Clojure is that Typed Clojure is a sound and practical optional type system for Clojure. Now, I started building Typed Clojure on top of some design ideas of Type Racket. So I identified that Type Racket had a meaningful subset of features that you might want in a Clojure type system. So I created a new type system based on Type Racket with specific features to type-check Clojure, and I present the design and implementation of that type system called Typed Clojure, and then formalize it and prove it sound. And I show that Typed Clojure's features correspond to real programs by evaluating over 19,000 lines of production Typed Clojure code. So this evaluation also brought about some shortcomings of Typed Clojure, or brought them to my attention at least. So the first shortcoming is that the users thought that there was too much of an annotation burden. There was too much manual effort to get ramped up to actually using Typed Clojure. So I created a semi-automated workflow to port Clojure programs, and I present the design and implementation of that along with a formalism and an evaluation where I use this workflow to port real Clojure programs to Typed Clojure. The second shortcoming is that there are certain programs involving macros that had incomprehensible errors because of some legacy brought over from Type Racket, where we have to expand code before we type check it. And I demonstrate how to improve the situation by extending Typed Clojure to support custom rules. And finally, there weren't enough functional programming. There weren't enough programs in functional programming style that were easy to check. So users wanted Typed Clojure to check more programs out of the box. And I show how to mix symbolic execution with type checking in order to check more programs. So part one of the talk and the thesis is the design and evaluation of the initial design of Typed Clojure. This part was published at ESOP 2016. And we're going to look at the design first. So let's contextualize our discussion with this top 5 features of Clojure. So we have functional programming, immutability, this ease of use idea, and host interoperability. So what we're going to do is show some Typed Clojure, show some Clojure programs that exhibit these features, and then show how Typed Clojure can check them. So here's a simple function that takes an x and a y coordinate, creates a record for a point, and you can see that you can extract the x and the y using this syntax. And actually, this isn't a record. This is actually a plain map. It just so happens to be a keyword map, which in Clojure usually means that this is a heterogeneous map. This map is designed so that it always has an x and it always has a y key. So in order to type check this, we have to model this in Typed Clojure. So I have this idea of a heterogeneous map, which is on the second line of this annotation here, and it basically says that a point has an x and a y entry that are both ints, and then I also have to add a annotation to point to give it its interface, and this will type check. And this demonstrates some rudimentary functional programming and immutability because the curly brace syntax actually introduces a immutable map. All right, so higher order functions are ubiquitous and really important in Clojure. Here's one that I just made up that allows you to combine the x and the y coordinate of a point using a function. So you can combine it with plus, you can combine it with string, and it has different behavior. To actually type check this, you use a polymorphic annotation. And this says that this function takes a point and a function of 2 arguments and then returns the result of applying that function. And this shows higher order functions, that's functional programming, and I think higher order functions are a big part of the ease of development of Clojure. Another idiom that's really important in Clojure is type-based control flow. So this function here coerces a string to an int. And you can see that there's an if statement to say that if it's a string, then call this Java method that's actually a method on the Java lang integer class to convert it to a string. You can see the 2 ways of using it down the bottom. And the way to check this is to use a union type and occurrence typing. And this is all straight from type racket. The idea is that you say that the input can either be an int or a string, and then occurrence typing automatically infers, based on the annotation of string question mark, that the then branch has a string and then the else branch has an int. This shows immutability because M is actually an immutable binding, and host interoperability because parseInt is a Java method. So here's exactly the same function, but in terms of an extensible multi-method. The idea is that it dispatches on the class of its first argument, and here's the then branch, which is now if it's a string, and the else branch is if it's a number. And to type check it, it's exactly the same annotation, has a union, and then we use string, occurrence typing tells us that in the string case it's a string, in a number case it's an int. And there's some functional programming going on here because class is used in a higher order fashion, and then there's some host interoperability. All right, so now let's look at how I formalized Typed Clojure and improved its sound. So I started with type rackets formalism of occurrence typing, and then I added some Typed Clojure features, namely I added heterogeneous maps and multi-methods, and then some Java interoperability, namely classes, fields, and methods and constructors, that kind of thing. And then I proved this fragment type sound, and has the important theorem is that well-typed programs don't go wrong. And intuitively, you can we encoded this idea of throwing a null pointer exception as a wrong state. So as a straightforward corollary of this theorem, we have that well-typed programs don't throw null pointer exceptions. At least the Clojure parts of them do. Like you might have a null pointer exception from Java that gets propagated up. But this is really important in a type system for Clojure because null is a idiomatic value to use. For example, in Scala, it's not idiomatic to use null, but it's also unsound to use null. You don't get this, this corollary. So it's an important result. Now let's look at how I evaluated the initial design of Typed Clojure. I performed an empirical evaluation of over 19,000 lines of Typed Clojure code at CircleCI. And we've already seen the good news, so here's the bad news of the evaluation. First, that there was not enough functional programming support to make functional programming like fun or enjoyable because there were too many annotations. You can see this first expression, all it does is bind f to be the identity function and call f on 1, but you have to annotate the identity, the fact that x takes an int. And the same with this map over here. We're mapping over a series of points, so clearly this p has to be a point, but we have to add this annotation. And users were not happy with this. This bogs down development because there's all this minutiae you have to do, and it's quite annoying. Next, there is a lot of annotations you have to write on the top level of Clojure. So not only do you have to write all of your own function interfaces, but also any libraries that you use have to come with types. And CircleCI found that these libraries didn't provide their own, so they had to reverse engineer their own types for this. And yeah, this reverse engineering libraries is not building your own program. And finally, there was there were a lot of poor error messages due to the expansion of macros. So here's a really simple function, expression. All it does is increment null, and this is a type error. So what happens, what does Typed Clojure say that this is? It says this is a static method error because it doesn't accept nil. So this is confusing. So I didn't call a static method. Inc is just a function. Well, the thing is that inc gets inlined into a static method call for performance. And this gets even worse when you have a much more complicated macro like the for list comprehension, where this it iterates over each element of the list, binding it to A. So A should be of type int, but unfortunately it's of type any, and we get a similar error. So it seems obvious that A is an int, but it's just not working out. But what you need to do as a user is to use this typed wrapper macro and then add an annotation. And this is a similar solution to type bracket. But you know, how is the user supposed to know that from such a cryptic error message? So yeah, this really bogs down development with these confusing error messages. So how did we do with the evaluation overall? So I think we did really well with immutability and host interoperability. There are some wins with functional programming, but unfortunately there are always also some downsides to using functional programming style in Typed Clojure. And the ease of development also suffered greatly from the type errors and annotations. So here's the rest of the talk is going to be about how I address these problems. So first, I address the annotation burden by creating a system for automatically annotating your programs. Second, I address the problem of incomprehensible errors from macros using an extensible typing rule system. And then I show how to check more programs by mixing symbolic execution with type checking. So now let's look at the automatic annotations. This is the first response to the evaluation, that there are too many annotations to have to write manually, and this part is insufficient. So here's the problem again. There are too many annotations, and we want to generate them. And how do we do it? Well, let's look at the design. The design is based on dynamic analysis. The idea is that the tool will observe your running program and then spit out a type that conforms to what it saw. So to show you an example, we're going to show how to annotate this program here to have this type over here in this type environment. So first, we instrument the program so that it's prepared to observe the program. Then when we run it, we have various tracking infrastructure to actually gather runtime samples. And then the idea is to convert those runtime samples into a type environment. So there's a naive translation, which basically is a direct translation from what it saw into a type environment. But now the type environment is quite large. We want it to be smaller. So there's a couple of strategies that we use to make it smaller. First is called local squashing, and the idea is if we have a type that's deeply nested but looks recursive, local squashing optimistically creates it into a recursive type when it's a good idea, or at least when certain parameters happen. And global squashing performs a similar idea, except it finds types that are spread across the type environment and brings them together so they're all in one place. So yeah, both of these squashing algorithms make the type environment smaller and more comprehensible. And this tool is actually the first part of a porting workflow. The idea is that you first generate your annotations, and then you immediately try and type check those annotations with Typed Clojure. And if there's a type error, you manually fix it until you actually type check your program. And the idea is that once you're done, you should be able to get some meaningful invariance about your program, because Typed Clojure is a sound system, and you don't have to necessarily have all the same annotation burden that you would have had without the tool. Yeah. So now let's look at the formalism of automatic annotations. It's going to be very brief. Here's the top level driver. It takes an expression E, which is basically a test, and then says, observe all the x's in this E. So for example, here's a function definition and a test. So all that f does is just take out the A entry. So it takes a map with an A and then takes out the and then looks up the A entry. So the way to plug this into this formalism is that you say, well, here's the test, here's the things I want to track, and then the output is this derived type over here. And this annotate, the insides of this formalism show how to instrument the program and do some efficient observations of the runtime, and then those various squashing algorithms that I explained before. So this process is intentionally unsound. These squashing algorithms actually combine types to create compact recursive type aliases, and this is an unsound process. And there's not much to prove about this formalism, and it's all tailored to work with this workflow. So really the evaluation is, the proof that this is a good idea is in the evaluation. So let's look at the evaluation now. So I evaluated this workflow by porting 5 open source programs from Clojure to Typed Clojure. Then I measured the kinds of manual changes that were needed to make sure that it wasn't too difficult. So for example, here's the automatically generated type for this function called mult. And here's what I actually wanted it to be. And it was close, but the problem was the dynamic analysis didn't see anything other than 2 arguments passed to mult. But the type errors, but using Typed Clojure as a feedback mechanism, I could figure out that while at runtime you could only see 2 arguments, this program must have more than 1 argument. And similarly, there's this function here that takes in a map of int to int, but actually it's a map of any to int, and the dynamic analysis didn't pick up anything other than int keys because of poor test coverage. So here's a function that has an interesting type. It's actually a recursive type, and it's automatically generated to be recursive. And it's called E, this def alias, and notice that there are recursive types in E, and if we didn't have local squashing, this would be a very long nesting of an expression. So this is what local squashing gives you. And global squashing actually lets us share this definition of E between multiple annotations. So this top-level annotation for parse X that says any to E, E is actually used in many other annotations, which really helps because the manual annotation, the manual changes needed was to add a couple of minor AST nodes that weren't covered in the tests. So I had to only add it once and for all because the global squashing basically reconciled the concept of an expression correctly based on its shape. So I found overall the manual effort was mostly deleting and upcasting types, or when it came to recursive types, just adding missing cases to recursive types. So let's go to our scorecard. Does this help? Well, the users were saying that there's an annotation burden, and based on this evaluation, I claim that automatic annotations makes porting Clojure programs easier. All right, so part 3 is about extensible typing rules, and it addresses the second complaint of the evaluation, which is that there are incomprehensible errors when it comes to type checking macros. So here's the problem. Again, we have this macro. It's difficult to, once it expands, Typed Clojure doesn't know what to do with it, so we get this incomprehensible error. And what we really want is to propagate type information so that the types are more precise, which gives Typed Clojure a better chance to actually type check this. The idea is to let the user define custom typing rules for their macros, so then this is an extensible system. But there's an immediate roadblock that actually dominates my contributions in this area, because Typed Clojure fully expands its code before it type checks. And this is something that's inherited from TypeRacket. And the idea is that you expand out to a small number of primitives, and then you only have to write a small number of axioms for those primitives. But that trade-off just wasn't working out for Typed Clojure. So to give you an idea, if you think of these expansions and type checkings as multiple passes over the same AST, then if we expand something up here and then check it again, if we wanted to check something before expansion, well, it's too late. It's already been done. So the problem is, how do we interleave these? So yeah, the solution is to allow Typed Clojure to interleave macro expansion and type checking, so it can expand things as it needs. So now let's move to the prototype. The idea is that the type checker gets control over the expansion. So the entry point to type checking is that to type check an expression, the type checker gets to decide whether to expand something or not. So it doesn't just get a pre-expanded expression. And to achieve this, I wrote a new Clojure analyzer that effectively allows gives the type checker all of the tools to safely expand a piece of code as needed. And this wasn't easy. There are a couple of reasons for this. I'll list some. So for example, Typed Clojure's top-level evaluation already interleaves evaluation and macro expansion. So bringing Typed Clojure into that was not obvious. How to manage all those things. I also had to maintain the correct lexical scope, which is not something that comes for free in Clojure. For example, in Racket we have syntax objects for that kind of thing. And then Clojure actually already has a type hinting system. So if you kind of add that up, I had to deal with interleaved macro expansion, evaluation, 2 type systems, and maintaining correct lexical scope. So this was fun. But once this was actually built, we could build type systems with it that allow custom rules for macros. So for example, here's an example type checker. It takes an expression and an expected type. And it says, if this is partially expanded, then here are some custom rules for macros. And yeah, this is it. So that was the prototype. So the problem was that there were incomprehensible errors in macros, and there's this existing technique of extensible type systems, of extensible types, typing rules to fix, to add type checking, to add more precise type checking to macros. So based on my experience with extensible rules, I think that it's very practical to extend Typed Clojure to type check macros based on these rules, and using that technique we can improve errors and we can again check more programs. Alright, so the final part of my dissertation and this talk is going to discuss symbolic execution, and it's the third response to the evaluation that in particular I want to check more programs, and I'm going to explain how I did that. So recapping, here's the problem. We have these programs that use functional techniques, like we have this identity function up here that's used, and then we're mapping over a series of points. The problem is there are too many annotations. So why do we need these annotations in the first place? It's because we're in the setting of bidirectional checking, and type checking proceeds from the outside in. So at this point, we have to have the type of X. At this point, we have to have the type of P. There's no way for us to delay this check. So the intuition to getting around this using symbolic execution is that there's actually a lot of information about the type of X and P adjacent to it. So for example, for X, the type of the argument of F is an int, and this tells us what the int is. And point is actually adjacent, it's in the same argument list. There are 2 points that show us that P is indeed a point. And the approach to realizing this intuition is to add a new typing rule for checking unannotated functions. And now the question is, what is the type of F on this second line? Well, the type of F is its function, its code. So F is a fun XX, but it's not just its code, it's code scoped over a type environment that it was defined in. So this looks a lot like runtime closures, and we're calling this a symbolic closure type because of that similarity. And the main difference is that instead of executing these closures with values, they're executed symbolically. Now the question is, how do we apply a symbolic closure? Well, we have enough information to just plug in the argument now. So yeah, that's the intuition of how to apply a symbolic closure, is that you have enough information at the point where you want to apply it to be able to just pull the rabbit out of the hat and then apply the argument. So there are a couple of key trade-offs that are going on here. First is this technique is undecidable. It very quickly becomes undecidable with more advanced programs. But the reason this is compelling for something like Typed Clojure is that many local functions are designed to be small, used once, and they're non-recursive. So they're actually quite easy to symbolically execute. And it turns out a lot of programs only need a small amount of symbolic execution for this technique to really help. And then we can rely on top-level annotations, which are already given, to drive the symbolic execution, and then treat the body of a function as sort of more morally type correct based on symbolic execution. Okay, so now let's look at the prototype for symbolic execution. Here's the gist of symbolic closures in 2 typing rules. There's an introduction rule and an elimination rule that look almost identical to runtime closures, except they involve type environments instead of value environments. And you can see that the introduction rule packages up the typing rule, the UAPS rule packages up the type environment with its code, and then the application rule first checks the function and then the argument as usual, but then we can unpack all the parts. We can say that in the definition environment with x of type sigma, which is the argument of which is E2 here, then the body of the symbolic closure is of type tau, which propagates out. And yeah, this is almost identical to the runtime closures, the reduction rules for runtime closures. So I created a prototype implementation of symbolic closures that I'm going to explain and demonstrate a bit about. It's just a small model that I wrote in Clojure. It exposes this one macro called TC, type check, and it takes an expected type and an expression, and it type checks the expression and returns the type. So for example here, 1 synthesizes a type of int, and then fun XX, if you give an expected type of int, we use the typical bidirectional strategy of starting x as int and then checking the body to be int. Now things get interesting when we emit the expected type of the function. So, for example, here we're just checking a function without an expected type, and we get out immediately a symbolic closure, and it says that under the empty type environment, this function has code funxx, and there's no type checking here. And this is actually a sound strategy because there's no opportunity to go wrong or to throw a type error, because this is just a latent computation that is not realized. So what happens when it is realized in like a application rule? So we follow that uapp rule that we saw a few slides ago, and populate x to be int, and then we symbolically execute the body, and then that flows out to the output of the application. So I've extended my prototype to also work with polymorphic types, and the idea is that the tool or the model looks at the type of the polymorphic type and deduces how the control flow has to work. So for example, if we're mapping the identity function over this collection, the type of map tells us that the collection actually flows into the x position, then the body flows out to the return type. And we can stack on this this idea by we can combine various symbolic closures together using more polymorphic functions. So like we could map over the composition of these two symbolic closures, and from the types we can deduce that the collection flows to the y, and the y flows to the x, and then x flows to int, all using symbolic execution. So to really test the limits of my tool, I reached for this strongly normalizing term of system F, which I'm going to call GR. It was proven untypable in system F, but it's strongly normalizing, so it's well behaved. It does. I figured out what it does. So here's what it does. It's just a quirky identity function, or at least you can use it this way. So if you want it to return 42, you give it a 42 wrapped in two functions. So here's an interesting challenge. To type check this quirky identity function that is using this GR term. So this is like the essence of why I think symbolic closures are really exciting, because the body of this identity function is untypable, probably in type closure as well, but the interface is fairly benign. So symbolic closures allow us to treat GR as a black box until it's executed symbolically. And if we plug this into the prototype, we start off the type checking by saying that x is of type A, and then stuff happens, symbolic execution. And then at some point x pops out and it's of the correct type. So it's morally correct because the symbolic execution engine told us so. So in this way, symbolic closures make the most of top-level annotations, even in situations that are as hopeless as this GR term that is proven untypable in System F. So our scorecard was demanding that we check more programs, and based on my prototype, I'm confident that extending type closure with this idea can check more programs. Alright, so in conclusion, I've shown that type closure is a sound and practical optional type system for Clojure. I presented the design of type closure, formalized the core type system, and proved it sound. And I've empirically shown that type closure's features correspond to real-world programs. I presented a tool to automatically generate annotations to ease the porting of Clojure programs to type closure, and I've tested it out by porting several real-world Clojure programs. And I've further identified and prototyped several extensions to improve type errors and type check more programs in type closure. Thank you.